All right, these are notes for section 2.6 for pre-calc. Our objectives for this section. First one, find the domain of rational functions and describe the graph's behavior near x values that are not in your domain. So we know that there's going to be some x values that we can't have. We want to be able to analyze what is the graph doing as we get close to those, knowing that we can't actually get to them. Second objective is to determine the transformations of the reciprocal function based on the equation. So when we learned back in chapter 1 those 12 basic functions, remember those? Yeah. The reciprocal function was one of those. So we're looking at if we have that basic starting graph, can we just shift it? Left, right, up, down, reflect it, stretch it. Can we just transform it into our new one? Our third objective is to find all asymptotes algebraically and look at what their graphs do and be able to state the limits. And then next week we'll look at analyzing graphs of rational functions for a lot of different characteristics there. So first of all, just a basic definition of a rational function. If we take two polynomials, so similar to the things that we've been finding zeros of, right? If we take two of those and just make a ratio of them, all right, so one's on top and one's on the bottom, f over g, we get a rational function. All right, rational functions are just ratios or quotients of those polynomial functions. The domain of a rational function is the set of all real numbers except for zeros of the denominator. All right, we cannot divide by 0, so anytime we have a denominator, which we will always have when we make a ratio, we have to worry about domain restrictions. Now it says every rational function is continuous on its domain. We encountered this again back when we were studying those basic functions. It doesn't mean it's continuous overall, but for the x values that we are allowed to use, it is continuous for those. So you won't have any holes in your graph, you won't have any breaks other than where there's a domain restriction. All right, so our first example. It says find the domain of f and use limits to describe its behavior at values of x that are not in its domain. So this is one of our pretty basic rational function. We just have 1 over x minus 2. But we have a denominator here that can't be 0. What would make it 0? So we don't want to have 2. So our domain for this function would be everything except 2. So if we write that in interval notation, we basically are just jumping over that 2. Now, without knowing what the picture looks like, let's see what happens as we get close to 2. So think of making a t-chart, and let's just pick two numbers that are really close to 2, one on each side. So maybe 1.99 and 2.01. All right, if we plug those into our function, 1.99 minus 2 gives us what? Okay, so we've got 1 over negative 0.01, or 1/100th. What's 1 divided by negative 100th? Negative 100. Okay, if we put a 2.01 in, subtract 2, we get 1 over 0.01, or 1 over 100th, which becomes 100. Okay, so if we think about our picture, as we get really close to that 2, when we're at 1.99, all right, so just to the left of our vertical asymptote, we're way down here at negative 100. Okay, and if we put in a 2.01, we're way up here at positive 100. Okay, so describing our limits. As we approach 2 from the left side, okay, we're using this 1.0 or 1.99 as an example. Our y value is negative and large. Okay, so as we approach 2 from the left, we've talked about that notation before, correct? Okay, so as we approach 2 from the left side, we are heading towards negative infinity. Our numbers are getting very large in a negative direction. As we approach 2 from the right-hand side, like this 2.01, our numbers are large and positive. So we're heading towards positive infinity. Okay? Now, what we created there, because on one side we're approaching positive infinity, on the other side we're approaching negative infinity, our graph is doing this, all right? We're going in opposite directions. We've created a vertical asymptote. So x equals a is a vertical asymptote of our graph if, as we approach from the left side or as we approach from the right side, we are heading towards positive or negative infinity. All right? That's our definition of a vertical asymptote. Our definition for a horizontal asymptote is a line that our graph approaches as we move away from the origin. So in this case, we are approaching negative infinity or positive infinity. We're going way off to the left or way off to the right. Is there some kind of horizontal line that our graph is approaching? All right, so let's look back at that example we just talked about. We had 1 over x minus 2. It's a basic transformation of our parent function, 1 over x. Which way did we shift it? 2 to the right, yeah? Okay, now, our basic function, 1 over x. Do you guys remember what it looks like? Yes, it has 2 branches. So normally it would look like this. Yes? We just want to shift that 2 to the right. So we're going to have that vertical asymptote at 2. Make sure you put asymptotes as equations, so x equals 2. And where is the horizontal asymptote? Where is there a horizontal line that your graph's approaching? Yeah. Okay, so if we are strictly moving this right 2, we haven't affected the horizontal asymptote. We did affect the vertical one. It used to be on the y-axis here, and we shifted it to the right. So what's going to happen to those branches is they're just going to move to the right too. Okay, does that make sense? Now, we would like to be able to have a fairly accurate placement of those. So let's look at a couple values on either side of our asymptote. We can't be at 2, but let's try 1 and 3. We're not going to graph our 100 and negative 100 that we found on the last slide. All right, those are too big. If we put a 1 in here, what do we get? If we put a 3 in here, what do we get? All right, so if we plot those points, 1, negative 1, all right, we're going to fix our graph here. Originally, our graph should have been here and here. All right, and then we said we have to shift that to the right 2, and it should land like that. Yes? Okay, sorry about the mix-up. So we did plot our points, 3, 1, and 1, negative 1, and they are verifying that we're in the right quadrants. Yes? All right. Apparently my brain's still sleepy. All right, so we've graphed it, we listed the asymptotes. Just a quick review of the characteristics of that parent function. We have y equals 1 over x. Domain and range both exclude 0 because we had those vertical and horizontal asymptotes here. It is continuous for all x not equal to 0. And it is decreasing for all of your domain. It's coming from the left here and going lower as we approach that y-axis. And on the right-hand side, it's coming up from way high and approaching 0. So it is decreasing in both of those branches. It is symmetric with respect to the origin, which makes it an odd function. That means we could spin it 180 degrees and it would look the same. It is unbounded. If you look at the whole thing, it is unbounded. Back when we did this in chapter 1, we did say there was an upper bound on the left and a lower bound here on the right, but overall, it's not bounded. We have no local maxes and mins. We talked about our two asymptotes being right on the axes, and the limit as we approach either positive or negative infinity is 0. So as we go out this direction, we are coming down towards 0, and as we go out this direction, we are coming up towards 0 from underneath. Okay? All right, so first one here says, sketch the graph and find an equation for h of x. It is obtained from our parent function, y equals 1 over x, by a translation of 5 units to the right, followed by a reflection across the x-axis. How would I put into my equation a translation of 5 to the right? What would that look like? Okay, so instead of just a plain x on the bottom, we have x minus 5. All right, just like our last one shifted 2 to the right, this is shifting 5 to the right. What do we have to do to make it reflect over the x-axis? A negative in front. Can I put that negative up here with the 1? Yes, it means the same thing. Okay, so where would our asymptotes be? Give me the equation. Yes, x equals 5. And then horizontal asymptote? Okay. Now, if we've done a reflection, instead of our branches being in quadrants 1 and 3, the thing from quadrant 1 will flip down and become quadrant 4, and quadrant 3 branch will flip up and become in quadrant 2. Yes? And then we're going to shift them to the right. So let's think about if we took one of those basic points, our normal branches go through 1, 1 and negative 1, negative 1. So if we shift it, they said they wanted us to go right 5 and then reflect over the x-axis. I would land here. Okay? And if I take my negative 1 point, right 5, and shift it over the, reflect it over the x-axis, puts it here. So I'm going to have a branch down here, and I'm going to have a branch on that side. Questions about that? Okay, take a minute at your tables and try the third example there. We are taking our parent function. We are translating it 4 units to the left, stretching it vertically by a factor of 3, and then shifting it down 2. Okay, example 3. We said we wanted to translate it 4 units to the left. What would that look like? Plus 4 with the x. All right, and then we want to stretch it vertically. Where would a vertical stretch show up? Okay, and typically it would be out front. right? It's in front of our parent function. So if you picture having this 3 out front, we could distribute it to the top and write it as 3 over x plus 4. Okay. And then the final thing is to translate it down 2 units. What do we do? Okay, with minus 2 on the end. Yes? So how does this affect our asymptotes? If we shift it 4 to the left, where would that land? At negative 4. So we have a horizontal asymptote at x equals negative 4. Where would our vertical, thank you. I was just going to say horizontal. Where would our horizontal asymptote be? Y equals negative 2. Yeah, we shifted down 2. Okay. Have we reflected it all? No. So we should still be in basic position of 1 and 3, those quadrants. All right. How do we do the stretch? So our branches are going to be stretched a little bit. Let's take our first point, which was 1, 1. We are going to shift it 4 to the left. We're going to stretch it by 3, and it's at a 1 right now, so it becomes 3. And then we're going to shift it down 2, and it lands here. So your branch would look like that. Instead of it dipping really close to where those asymptotes intersect, it's just pulled away a little bit. Our other point was the point negative 1, negative 1. We're going to shift it 4 to the left. We're going to stretch it vertically by 3. Instead of being at negative 1, we're down at negative 3. And then we're shifting down 2. So we'd have a branch over here. So the bigger this top number gets, as this gets larger, your branches just pull away. And I'm going to say pull away from the origin. It's going to pull away from wherever those asymptotes intersect, the new origin type of a thing. So if this had been, say, a 10, we would have just had a branch that was further out here. It wouldn't dip in quite as far. Okay? So if we can write them in this transformation format, you guys know what happens. You can tell what transformations are done. The question comes now is, what if they're not in that format? What if we have a polynomial like this, where there's some x's on top? All right, that changes things a little bit. It says, the graph of any non-zero rational function of this format can be obtained through transformations of your reciprocal function. If the degree of the numerator is greater than or equal to the degree of the denominator, in other words, as long as the top degree is the same or higher, we can rewrite it using polynomial division. We can transform it into that transformation format. All right, so does the first one look like the types we've been doing? Can you identify the transformations? Okay. Go ahead and list the transformations and tell me where the new asymptotes would be. We'll tackle the limits when you come back as a class. All right, so I'm going to pause the video. Go ahead and find the asymptotes and what transformations happen. All right, let's check. Did you list a vertical stretch by a factor of 2? Yes? That's coming from that top piece. And then going left 3? Yes? Okay. What would the vertical asymptote be? Oops. and horizontal asymptote. Have we moved up or down at all? Okay, then we're still at 0. All right, vertical asymptote at x equals -3, horizontal at y equals 0. One option, if you don't want to have to shift your points in all the different transformations that happen in each graph, we can always go back to just a table of values. We know we can't have x being -3, so let's pick a number on either side of that. So let's use -2 and -4. Plug those in and see what you get. If we put -2 in for x, -2 plus 3 is 1. 2 divided by 1 is 2. If we put -4 in there, add 3, we get -1. 2 divided by -1 is -2. Let's see if that lands where we think it should. Now, keep in mind that when you're graphing points, you are still going from the main x and y axes, right? You're not going from the new asymptotes. So -2, 2 is here, and -4, -2 would be here. So does that seem logical? It's pulled a little bit away from the original point, but it hasn't been reflected or anything, so we're still in basic quadrants 1 and 3. Okay, the last thing they asked us to do is to use limits to describe the behavior. We're going to have 4 limit statements. Okay, one is we go to -infinity, one is we go to +infinity. Then we're also going to have what happens as we approach the vertical asymptote from the left, what happens as we approach the vertical asymptote from the right. Okay, so the limit as x goes to -infinity. What's happening as my x values get further and further this way? My graph is, but it's not going higher continuously, right? I mean, it's approaching a limit. What's it approaching? 0. It's coming up towards that y equals 0 line. Okay, so we are approaching 0. What happens as x goes towards +infinity? As my x's get bigger and bigger over here, I'm still coming down towards 0, right? Coming down from the top side, but I'm still approaching 0. All right. What happens as I approach -3 from the left? As I'm coming towards this vertical asymptote from the left-hand side, my graph is going where? Down towards -infinity. Okay, what happens to my graph as x goes towards that -3, but from the right-hand side? So I'm coming from the far right, and my graph is saying go way up towards +infinity.
Why are you putting the plus and minus sign to indicate that you're going from the left? Like just above the 3 or?
Here. Yep, it's like a little exponent of your number. You don't want to put it in front because that means you have a positive or -3. We are approaching -3, but on the left and on the right.
So the left is negative and the right is positive.
Yeah, this would be on the left. This would be indicating you're coming from the right-hand side. Okay? All right. Does our next example look like you can tell what the transformations are? Eventually, you're right. Eventually, because we always can do it, right? There's always going to be a way to figure this out. But right now, I can't tell. The bottom looks not too bad, but the top is not with just an A value. It's not my plain vertical stretch or compression piece. Okay, so what we have to do is divide it out. We're going to do this one long division just to refresh your memory. So if we take 3x divided by an x, we get 3. I'm going to put a 3 on top. When I multiply 3 times x minus 2, I get 3x minus 6. And then what do I do with those? Yep. Subtracting 3x minus 3x is gone. Negative 7 minus negative 6. It's negative 1. And that is our remainder, right? So we would write our answer and say h of x equals 3 plus, we have this remainder piece. Yes, it's a negative 1. It's trying to be divided by x minus 2. It's just not big enough.
So weird that you're writing with the green pen when it's red.
What if I turned this around? What if I put that 3 off on the right-hand side? That's equivalent, right? But now it's in transformation format. We can tell what's happening to the graph. What are the, I know, Carter, it just blows your mind, doesn't it? What are my transformations?
Right, too.
I really wish the recording was getting your facial expression right now. Okay, reflect over x. I heard right 2 and up 3. Yes? Okay, so where would my new asymptotes be? Okay, I have a vertical asymptote at x equals 2. Horizontal at y equals 3. And we've reflected, yes? So we should, instead of being in quadrants basic 1 and 3, think of 2 and 4. All right, let's pick a number on either side of 2. So 1 and 3. All right, if we put a 1 in here, and you can put it into the original function or you can put it into our transformed one. If we put a 1 in here, 1 minus 2 is negative 1. Negative 1 divided by negative 1 is 1 plus 3, 4. So we have the point 1, 4. Yes? So we have a branch here, which is what we were expecting. And then if we put a 3 in here, 3 minus 2 is 1. Negative 1 divided by 1. Negative 1 plus 3. All right, so does it look like we flipped it over and we shifted it right and up? Okay. Limits. So what is happening as my graph goes off towards negative infinity?
No, it's approaching 3.
I'm not approaching 0 anymore. I'm approaching 3, right? That's the definition of our horizontal asymptote. It's a line that your graph approaches as you move far out. So we are approaching 3 both as we go towards negative infinity and as we go towards positive infinity. Okay, you should be approaching that horizontal asymptote. What happens as we approach our vertical one? So let's approach 2 from the left. As we come from the left side, our graph is going up. So we're approaching positive infinity. As we approach the 2 from the right-hand side, my graph is heading down. So I'm going towards negative infinity. Questions? Okay. The next one, we're going to have you try. You do not have to do long division on this. How do I know? The degree on top is smaller than the degree on the bottom, right? We only use the long division process if the top is equal or bigger. So there should be a way to rewrite this so it looks more like our normal transformation equation. So think of factoring the denominator and see what you can do to reduce. All right, my suggestion was to factor the denominator, yes? Guys? Factoring the denominator, what can I take out of this? I can take a 2 or negative 2. Why would it be better to take a negative 2 out? You already have your x being positive, right? And we want this to look like it's x plus or minus the number. So if we factor a negative 2 out, we're going to get negative 2 plus x. Now, can we reduce that 6 and that negative 2 that are outside? Yes. It becomes negative 3 over, and then can I just flip these two around and write it as x minus 2? Okay, so what transformations are we doing? What's the negative in front do? Okay, we have a reflect over x. What's the 3 do? And at the bottom, right 2. It becomes x minus 2, so right 2. Okay, so where would my asymptotes be? I heard x equals 2, that's your vertical one. And we shifted, did we go left or up and down at all? So horizontal is still at 0. All right, now we have done a reflection. So again, we're thinking positions, quadrants 2 and 4. And then we've stretched it some. All right, so let's try 1 and 3 again since we can't be at 2. And again, you can go back to the original function and plug them in. We've got 2 times 1, that's 2. 4 minus 2 is 2. 6 divided by 2 is 3. Putting a 3 in here, 2 times 3 is 6. We've got 4 minus 6. So negative 2. 6 divided by negative 2. Thank you. All right. I know, it's pretty tough math in the morning. Does it seem logical? We're in the right quadrants, and we've stretched it so we're further away. Instead of just being 1 dot up, we're 3 because we stretched it vertically. Okay. Limits. What are we approaching as we go towards positive and negative infinity? 0. We're approaching that horizontal asymptote. Okay. What are we approaching as x goes towards 2 from the left? We're going to infinity. What is the limit as x goes towards 2 from the right-hand side? All right. Questions at all about that? All right, we have one more example to try. This one looks different. What's different about it?
Oh, they don't have it up and down. They have it.
Okay, we can rewrite it.
Oh,
All right. It is quadratics, yes? So we don't have linear polynomials anymore, we have quadratic ones. It says just find the horizontal and vertical asymptotes and then describe the behavior of your function using limits. Okay? Where did we look for domain restrictions? At the bottom, denominator. All right, that's what created the vertical asymptotes. So, does x squared plus 1 ever become 0?
No, because it's imaginary when you factor it.
Right, if we tried to factor this or solve for x, we're getting imaginary pieces, correct? So, we have no vertical asymptotes since that can never happen. Now, for horizontal asymptotes, we're going to try to change this into that transformation format so we can see if we've moved up or down at all. We're going to take x squared plus 2 and divide it by x squared plus 1. What happens? X squared divided by x squared is 1. 1 times that is x squared plus 1. And what do we get when we subtract? Yes? So if I were going to rewrite this, I would say my answer, my function, is this 1 on top plus my remainder. Yes? Okay, now, our definition of a horizontal asymptote was a line or graph approaches as we move either towards positive or negative infinity. Okay, so as we move far out. So picture what happens to this function as this x approaches positive or negative infinity. If it gets really, really large, whether positive or negative, we square it, it's going to get even bigger, right? We add a 1, it gets a little bigger. So right now we have this huge number on the denominator part. What's 1 divided by this really huge number? A really, really tiny number. So what are we approaching for my y value here? We're approaching this 1, right? This goes to 0. All right, that whole piece is going to get so tiny, it's not really going to affect my graph a whole lot. I'm going to just have the 1 left. So my horizontal asymptote is just this, y equals 1. Okay, and if we looked at a graph of this, notice our window here. We're going from -1 to 3, so each of these tick marks is just a 1. So we do have a horizontal asymptote at 1. Our picture shows there's no vertical asymptotes anywhere. Okay, it's just a nice continuous curve. So what is the limit as x approaches negative infinity? As x approaches negative infinity, what's my y doing? It's getting close to 1. As x approaches positive infinity, I'm also approaching that 1. Okay? But this time I'm approaching 1 from the top on both of them. Okay? Because this part here will never be negative. I'm never going to be able to come up from underneath it. Okay? So, just to summarize, characteristics of our rational function. Our end behavior, which is this limit description that we've been doing. The first statement says, if n is less than m, well, what's what n and m? N is our degree on top, m is our degree on the bottom. They're saying, if the top degree here is smaller than the bottom, we have a horizontal asymptote at 0. That's like those first few graphs we did where it was just a constant number on top and then we had something like x minus 2 on the bottom. Okay? We didn't move our graph up or down at all. We just approached 0. What if our degrees are the same? It says use this. What's a sub n and b sub m? Those are our leading coefficients here. Okay? Now look back at this example. Top degree is 2, bottom degree is 2. They match. What are the leading coefficients? 1s? What's 1 divided by 1? And that was our horizontal asymptote. Yes? I made you do long division. We could have done it just with degrees.
So now look
I was hoping some of you might remember that from Algebra 2. If the top degree is bigger, right now we're going to say there's no horizontal asymptote. There is a different kind of asymptote that we'll talk about next week. It's a fun one, and it does require long division.
This isn't a democracy. We also voted you off the island, but we didn't get it.
Vertical asymptotes. It says these occur, listen please, these occur at real zeros of the denominator, right? We looked at the denominator, what makes it 0? It says provided that the zeros are not also zeros of the numerator of equal or greater multiplicity. What that's telling you is you just want to make sure you have reduced any common factors. All right, and what I mean by that is, let's say our polynomial, if we factored it, was x minus 2 times x plus 1 over an x minus 2 times an x plus 5. Okay? This x minus 2 drops out. So it is not a domain restriction. Okay? It's not going to be a vertical asymptote, and it's not going to affect our x-intercepts either. Okay? So for both of those, we have to get rid of those common factors first. All right? Then anything that makes the bottom 0 would be a vertical asymptote, and anything that makes the top 0 would be an x-intercept. Okay? Y-intercepts are found strictly by plugging a 0 in for all of your x's. And again, we'll look at more of that next week. All right, so for today, you are doing 1 through 9 odd, 11 through 18, and 20 and 21. I will get some graph paper handed out to you here.